In this video, we will present our paper with the title is Stability Analysis of Ferrofluid in the Container for Levitation in 2D using Python MyPy library. We are from Department of Physics, Universitas Negeri Malang. Background to the problem: magnetic levitation of ferrofluid in the form of droplet in the reference 1, a capsule in reference 2, and a box reference 2 using dynamic stabilization. Dynamic stabilization need microcontroller or computer change magnetic field through electromagnetically. Electromagnetically needs external high power energy. Some apparatus from reference 1, 2, and 3 will be shown in this representation. This is from reference 1. This is a coil, and the current is controlled by some amplifier, and this is a displacement sensor. This is to know where is the position of ferrofluid droplet. In the second, we see a capsule, and this is electromagnetic. This is controlled by the computer, and this is some sensor to know the levitation. And this is using Q coil. This is a copper coil, and this is a 2-cylinder. We need an efficient system, not using electromagnetically. System to propose: using 2 source magnetic permanent. Change the distance to change the magnetic field. In this paper, we want to analyze it for stability in 2D numerically using Python library MyPy. The theory in NNP in fluid: if magnetic nanoparticle or MNP is subject to external magnetic, there are 2 forces acting it. First, the magnetic force Fm from the external magnetic field, using this equation, into the fluidic force Fs, MNP moving in fluids. This is a Stokes equation. Other force, buoyancy, gravitational, and interaction between particles are neglected according to reference 5. The orientation of NNP at no external magnetic field is random. When the applied external magnetic NNP, external magnetic applied, NNP will follow the field direction. This is the external field magnetic H, and this is the MNP follow the direction of H. In static condition, we must eliminate Fmx mid H is strike up. It get sigma Fm equal to sigma Wm plus Wg. So we have Fmct equal to Wmt plus Wg. So it means that if we have H like this, we must arrange to H to strike up, and is this same direction of FMG like this. We must remove this direction of FMH. So this is VM, this is 1 MNP, and VMT is mean total of MNP in container. And WG is the weight of the container. T is total index. The method that we are using is numerical. We arrange two magnetic sources facing each other by varying the poles. In the middle of the two magnetic sources, it places a box containing ferrofluid. Calculating HZ on the upper and lower bound of the box. Grab the normalized HZ along the boundary. Two magnets facing each other with 15 mm distance like this. This is 15 mm. Ferrofluid is in the middle of two magnets. This is ferrofluid. Calculated H on lines L1 and L2 from -40 mm to +40 mm. So we are calculate the value of H in this L1 and L2. The research result in configuration 1, different pole with the direction direction H is up. This is the result of simulation. This is a different pole, and we are arranged to H to strain up to the direction is up. This is L1, this is L2, and this is the result of computation. Remember, the ice is normalized, so the value is 1. Why we are normalized? Because it is easier to see the graphical. In configuration 2, symbols north is not with the direction H are opposite. We see this, and this is the distribution. This is L1 and L2. Configuration 3, symbol south with the direction H are opposite. This is the same result with configuration 2. Configuration 1 with different pole with the direction H is up, direction H is up. At position -10, between -10 and +10 is highly linear. This is linear. From 10 minus or positive to -40, and this is positive 40 is not linear. So this is the ice is not linear, and we don't know the equation. Maybe this is quadratic or exponential, we don't know. But for sure, this is non-linear. The width of ferrofluid is 20, and the width of we are measuring is 80. This is mean is equal to 1/4 or 25% smaller than the width of the magnetic source. You know that magnetic south is 80. Configuration 2 and 3, different pole with the direction is opposite. There are no linear distribution. So this configuration cannot, or it is very difficult to use as a basis for levitation. Conclusion: magnetic levitation for ferrofluid in the container can be done easily if the magnetic field is uniform against the direction of gravity, with a container size is 25% of smaller from the size of the uniform magnetic source, and it must be located at the center. Thank you for your attention. If you have any questions, suggestions, and questions regarding this presentation, I would really appreciate it.